So today we're going to talk about universal hashing, which is an approach for making sure that somebody cannot break your hash table. Break it in a specific way called creating a pathological data set. So as a reminder, what are hash tables? Well, the most important aspects of hash tables are that they really just do these three things: insert, delete, and lookup, and they do those very fast. So they do them in constant time. But they only really do them in constant time if you've got a reasonable hash function and a reasonable scheme for handling collisions, and if your data is non-pathological, so it's not specifically designed to break your hash table. What are they not good for? Anything that's going to require like random access or some sort of order. So going things through in a specific order or accessing elements at random. They're not really meant for that kind of access. All right, before we get too much into pathological data, I do want to just define a couple of things. So the first is going to be the hash table load factor, which we usually denote with alpha. And that's going to be the number of objects in the hash table over the number of buckets. So if I have n buckets and I have my set S that's in the hash table, that tells me sort of how many of the buckets are filled, what percentage of the buckets are filled. All right, so first question, what is the maximum possible alpha value, so the maximum possible load factor for separate chaining? And of course, really what I mean by this is what's the maximum load factor of a hash table implemented with separate chaining? Well, technically, I could have as few as one bucket in a separate chaining style hash table, and I could have a bunch of objects in it. So really the ratio here could be sort of theoretically infinite if I have an infinite number of objects and just a single linked list that all those objects are in. So there's really no maximum or cap on the load factor of a table with separate chaining. That said, if you get over 1, that means you're going to have to search on average through some linked lists. You're not going to get lucky enough to have just one value at every single bucket. What's the maximum possible load factor when using a hash table that's implemented with open addressing? Well, in open addressing, you store the values directly inside the table, and if you have n buckets, that means you can have at most n objects in the buckets. So your maximum load factor for open addressing is 1. All right, so in general, though, you want to make sure that alpha, your load factor, is constant. So you don't want it to be something on the order of n or 2n, for example, if you're going to have the hash table operate in constant time, so the insert, the delete, and the lookup. For open addressing, you really want it to be much less than 1. And maybe I should just put less than 1 here. 0.75, so 75% is a reasonable rule of thumb. If you have an open addressing hash table that's at least or less than 75% full, you're not going to have greater than constant time lookups in general. Thus, for a good hash table performance, you have to control the load. So how do you control the load? You implement a hash table. What do you have at your disposal to control the hash table load? Well, your only real option is to change the denominator here. So change the number of buckets. So you can always increase n to reduce your load factor. You can't really change this. If you start dropping items that somebody wants to insert into the hash table you've implemented, they're probably not going to use your hash table. So in general, how do you do this? Well, let's say you have your hash table that has n buckets. Once your load factor gets greater than or equal to, let's say, 75%, you're just going to copy everything over into a larger table. So maybe this is n times a factor of 1.5, in which case you'll have reduced your load factor. Okay, so that assumes that the person that's using your hash table is playing nice, and that's not always going to be the case. So what you're trying to do is create hash functions that spread the data out in your table. And another way to say that is that you're trying to minimize collisions. Unfortunately, it's not possible to create a hash function that always does this, and we'll talk about why in the next video. But just know that the sad fact of life is that it's impossible to create a perfect hash function that will always spread the data out. Another way to sort of summarize that is that you can always create a so-called pathological data set for any hash function. So if somebody constructs a beautiful hash function, you can always break it and say pick only the things that map to the same value every time.